Welcome to Lab 2. Today we will be measuring the power of the laser beam, the beam diameter, and the beam divergence. These are three important characteristics of a laser beam because the beam diameter is a very important measure. The reason why it's an important measure is the beam profile almost looks like a Gaussian with the edges tapering very slowly. Therefore, different people may tend to measure the beam diameter at different points. Therefore, it is important to specify where the beam diameter is measured. So, all the engineers and scientists came to a conclusion that they will measure it at a point which is called 1/e² point of the P maximum. That is to say, if you take the maximum power and then you multiply that by 0.35, and that gives you a point on either side, and we will measure the beam diameter at that. Secondly, if you talk about the measurement of the power of the laser, if the laser is directly put onto the detector head, the detector head usually, the active area of the detector head is larger than the beam diameter. So, what really happens is that it will be saturating the detector, therefore, we need to fill the detector. That also we will be talking. And then finally, an ideal laser should have no beam divergence at all. But a real laser is far from an ideal laser. It will have a beam divergence. We will define what is beam divergence, and we will show how this can be measured. So, these are the three important parameters of a laser beam. So, if we now come to the first part of the experiment, where we will measure the intensity of the beam. We have a laser, we have a lens here, and then we have the detector head, and then the meter we will show in the next slide. So, why is a lens here? As I mentioned earlier, if you have got the beam directly put onto the head, the beam is much smaller than the head size. Therefore, the two things will happen. Number one, the detector head will be saturated. Second one, the entire area of the laser head is not used. Therefore, we need to put a diverging lens here, and that diverging lens will allow the beam to be exactly equal to the active portion of the detector head. Then it gives the correct reading. When the beam is broader than the detector head, also we get wrong reading. So, in this one, next slide, we are showing the detector head and the power meter itself. This meter is nice meter wherein you can set the wavelength and you can set the power levels. This can measure from microwatts all the way up to a few watts. This can measure, but remember, depending on what laser we use, we have to set it for that particular wavelength. If it is a helium neon laser, of course, you have to set it for that wavelength. If it's a diode laser, you have to set it for that particular wavelength. And then you diverge the beam and measure exactly. If we now go to the table, this table has three columns, as you can see. Number first one, you measure the beam diameter as it is without any lens in between them. Therefore, it gives you a reading, but which is a false reading. Then in the second one, you can measure it by diverging the beam to exactly equal to the active head size. That gives you the correct reading. Then the third one, we can overfill it also and then measure it. So, the first and the third readings are the wrong one, and the middle one is the correct one. The next part of the experiment is to measure the beam diameter. We can use the same setup, except that we will have a knife edge put on the top of a lab jack. This knife edge can be moved using a micrometer, which I will be also showing when we show the experiment itself. So the idea is, first of all, block the beam by using this blade to completely block the beam, and then slowly withdraw the knife such that the beam is allowed to fall on the detector. So as you slowly start withdrawing, more and more intensity will be there, and if you plot a graph between the distance and the intensity, this shows like this part of the curve in the next slide from here to here. So once you do that, because this curve is symmetrical, you can complete this one also, and then measure the P maximum, the maximum power, and then from the maximum power you can mark the 1 over E squared points and then measure the intensity at those points. So the table shows that we have, yes, the table shows that we have different points at which we will be measuring the intensity, and then we will draw this part of the graph. Yes, this one is the translator. I wanted to show a figure of the translator also, and the actual translator we'll be seeing in a minute, and that's where the table is. And the last one is the beam divergence, which we are talking about. This is the beam divergence, and this is of course an exaggerated picture of a beam divergence. Beam divergence will be this, not this much, and you can actually measure the diameter at different distances, and you can call them D1 and D2 as the two points at which you measure the diameters. These distances correspondingly are L1 and L2. At this point, I would like to make a mention before we go to the next slide showing the beam divergence itself. There are two types of beam divergences. One is they call the near field, the other one is called the far field. The near field divergence is something, the divergence is measured very close to the laser head. Unfortunately, what happens is, in some cases, the output mirror of the laser will have a concave surface such that the beam first converges and then diverges. So therefore, it gives you a wrong reading. And the far field divergence is where it is measured very far away. In the text, you will see that these are defined as the divergence. The near field is simply as near to lambda over d squared, and the far field is lambda over d squared times 100. So technically, you should measure in a far field divergence situation, but in the lab sometimes it will be difficult to do such a long distance. It will be tens of meters. So for demonstration purposes, we can measure the near field divergence itself. So the equation for the divergence is given here, theta equals to d2 minus d1 over L2 minus L1. So this is a fairly simple thing. First measure the diameter at one distance, and then measure the diameter at the second distance, and then find out d2 minus d1 at L2 minus L1 and find out the angle divergence. So this experiment, like I said, is something which we can very simple and easy way to measure the properties of the laser beam.